When interrelated components operate without centralized control or feedback mechanisms, the result is chaos. A single misaligned part on a high-speed line halts the machine and triggers a cascade toward total operational failure. This basic flow diagram illustrates the engineering solution to that chaos. A system is a set of interdependent components working to achieve a specific goal. It relies on a continuous loop, taking data as input, passing it through processing to create meaningful output, and using feedback to adjust its control mechanisms against the outside environment. For your exams, remember the 6 baseline characteristics of any system using the acronym OIICA: organization, interaction between components, interdependence, integration into a cohesive whole, a central objective, and adaptability to environmental changes. Systems are further categorized by how they interact with their surroundings. Open systems, like a business, exchange data with their environment, while closed systems, like a thermostat, are self-contained. They can also be classified as physical, like computer hardware, or abstract, like a mathematical equation, and man-made versus natural. To maintain stability, these systems rely on control feedback. Positive feedback amplifies an output, like rising stock prices encouraging more buying, while negative feedback reduces output to correct deviations and keep the system on its intended target. Modern business systems are highly interdependent. Attempting to automate a manual workflow without first analyzing these inputs, outputs, and feedback loops simply digitizes existing flaws, accelerating the speed of failure. To prevent this, engineers rely on a structured framework. That framework is the System Development Lifecycle, or SDLC. It replaces disorganized coding with a strict, phase-gated engineering methodology. This flowchart details the complete 7-step SDLC pipeline. It begins with the recognition of need and progresses systematically through feasibility, analysis, design, implementation, testing, and finally, post-implementation maintenance. This progression is strictly chronological. Notice that actual implementation and testing do not occur until phases 5 and 6. The SDLC prioritizes logical planning and structural design first, meaning hardware and code are the final pieces of the puzzle. Every major concept in the syllabus, from feasibility matrices to logic modeling, acts as a specialized tool deployed at a specific stage of this 7-step scaffolding. Phase 1 begins with needs identification. Analysts determine why a system is required by categorizing demands into 3 tiers: operational needs for daily processing, management needs for reporting, and strategic needs for long-term policymaking. Once the need is identified, analysts perform a feasibility study using the TELOS framework: technical, economic, operational, legal, and schedule constraints. Technical feasibility asks if the required hardware is available. Economic feasibility asks if financial benefits outweigh costs. To answer these questions, analysts conduct fact-finding. They gather documentation about the firm's organizational structure, assess the user staff's skill levels, and map out the daily workflow to spot bottlenecks and inefficiencies. Analysts choose their information-gathering tools based on the type of data required. Face-to-face interviews provide deep qualitative insights, but consume massive amounts of time. Questionnaires provide quantitative data at scale, polling hundreds of users simultaneously to find broad trends. By utilizing fact-finding and the TELOS framework, Phase 1 acts as a filter. Its primary function is to identify and stop unviable projects before committing resources to development. Projects that survive the feasibility check move to Phase 2, analysis. Here, the goal is to create a map of exactly how data currently moves through the organization's existing system. Analysts model this using a data flow diagram with 4 Jordan-DeMarco symbols. The circle represents a process. The rectangle is an external entity. The open rectangle is a data store, and the arrow represents the data flow. Structural rules govern every DFD. Every process must have at least 1 input and 1 output. Furthermore, a data flow cannot connect 2 external entities directly, nor can it pass directly between 2 data stores without a process in the middle. This level 0 context diagram treats the system as a single process interacting with external entities. To view internal mechanics, analysts use explosion. Cracking open that level 0 process generates a level 1 DFD, mapping the intricate data flows between subprocesses.
To ensure every data element flowing through these diagrams is standardized, analysts create a data dictionary. This centralized metadata repository defines the precise name, type, length, and range of every piece of data in the system. Data flow diagrams and data dictionaries illustrate where information travels and what format it takes. However, they do not show how internal conditions evaluate that data. To document specific business rules, analysts need logic modeling tools. To document the decision-making rules hidden inside a DFD process circle, analysts utilize logic modeling. This decision tree maps actions based on specific conditions, used when the exact sequence determines the final outcome. Tracing from left to right, the system evaluates income first. That result dictates if credit score is evaluated next, leading to the final approval or rejection. For complex intersecting rules, analysts use the decision table. Each column represents a Boolean combination of conditions. In Rule 1, an income over $30,000 paired with a high credit score results in approval. In Rule 4, failing both conditions results in rejection. For scenarios involving heavy procedural actions or repetitive loops, analysts use structured English. This technique uses simple verbs and data dictionary terms to describe logic without resorting to actual programming code. These trees, tables, and structured English descriptions eliminate ambiguity. They ensure that when the blueprints are handed over, programmers build the exact decision-making logic the organization requires. With the analysis complete, the project moves to Phase 3. Here, the proposed system must justify its own existence through a rigorous cost-benefit analysis. Management compares the anticipated development, hardware, and operational costs against the expected benefits. These benefits can be tangible and quantifiable, like reduced staff costs, or intangible, such as improved customer satisfaction. To secure approval, analysts must provide financial proof. They calculate the net present value for the time value of money, the payback period to show when the project breaks even, and the return on investment to prove the net benefit. Once the financials are secure, system design moves from technology-independent requirements to the technical constraints of hardware and databases. This is where the logical design, the blueprint of what the system will do, is translated into the physical design. The entire process culminates in the system proposal. Executives will authorize the physical build only if the logical design is sound and the financial formulas promise a clear return on their investment. Following approval, the SDLC enters its final technical phases: implementation, testing, and quality assurance. Implementation is the shift from theoretical blueprints to tangible execution. Programmers write the code, network engineers install the physical hardware, and data is migrated from the old system to the new one. After implementation comes system testing. This is a systematic verification process designed to prove that the newly constructed physical design accurately executes the exact requirements defined during the analysis phase. This 7-step journey provides a clear engineering path from identifying an operational problem to launching a fully verified physical system. The rigor applied in the earliest steps, evaluating feasibility and mapping data flows, ensures stability at the end. These early constraints prevent minor logical flaws from compounding into massive software failures during the coding phase. True expertise lies in knowing exactly why a specific logic tool or financial formula is the correct choice for a particular phase of the SDLC. Mastering system analysis and design means utilizing these discrete tools to manage and conquer technical complexity.